I want to catch us up on where we left off. And we're starting a module today. We'll spend some time on a particular type of motion today. Let's go back and remember kind of meandering lecture I gave in the last class about the Born-Oppenheimer approximation. The big end point of that whole discussion about elephants and flies is that motion, the energy levels, if you will, of a molecule split into categories of very distinct energies. I call that the James ladder of spectroscopy, or the Born-Oppenheimer hierarchy. And the idea is that molecules, we don't need to think about them as a soup of electrons necessarily and nuclei, only when we need to think about the electrons themselves. But if we just think about things that the nuclei do themselves, so atoms as an object, not as a soup of charges, but just as an object, a mass. There are other types of motions that they can have, right? They can have translational motion, that's part of one box motion. It's ideal gas motion. Rotational motion, we'll talk about rotation after vibrations. There's a reason why I'm not doing it in this order. And then there's of course, there's 3 rotational degrees of freedom. I'll show you that when we talk about rotations. A 3-dimensional object has 3 different axes it can rotate on. A really great example of that is a hammer. I'll cover a hammer and look it around and look at the different axes. And then the most important part, really the most complex, it's not really the most complex, but of the nuclear levels is the vibrational levels. And there are, it's a molecule dependent quantity how many different vibrations there are. It comes to the number of atoms. And for a 3-dimensional molecule, it's 3 n - 6. So for a molecule of just 2 atoms, we actually have to fix this number. That would mean it has 0 vibrations. But of course, a molecule that has 2 atoms has 1 vibration, just a stretch. So I'll have to fix that number for N = 2, for instance. But for a 3-dimensional molecule, this is totally reasonable. If you think about benzene, for instance, benzene has 6 hydrogens and 6 carbons, 12 atoms. It has 3 × 12 - 6 vibrations, which is 12, 24, 36. It's 30 vibrations, right? 30 unique different ways to vibrate the molecule. We'll look at very complex polyatomic molecules later. First, what we should appreciate is a single vibration molecule of 1 mode. So that's what we'll focus on today in particular, and then see how we can take the theory of 1 vibration and extend it to a system with 3 n - 6 vibrations. Right? And then finally, everything else is just in the electronic motion, the electronic structure of the molecule. Those are the transitions of the energy levels we associate with atoms, for instance, 1s and 2s. Maybe you guys remember from organic chemistry, sigma and pi bonds and orbitals. That's what the electronic structure references. It references the states that the electrons are in the molecule. And of course, if we're thinking about exciting the electrons or ionizing them, that will matter. That structure is very sensitive for the electrons. But if we're just thinking about nuclei moving in space, we don't have to think about anything. That's what the power of Born-Oppenheimer is. Ignore it and then just deal with it when it comes up. Right? We'll see how that all of these organize nicely once we do all of them. We'll see that they all kind of connect to each other and they build a natural hierarchy of energy. Okay, so let's talk about vibration today. And we're going to keep it simple. We're going to keep it simple today. And think of systems with just 1 vibration. We're going to think about really complicated things, and we certainly will at some point. I think it's best that we tackle the problem of a single vibration first, a molecule that only can vibrate 1 way. So, of course, there's only 1 type of molecule that does that. That's a diatomic molecule. So we're going to think about, consider a diatomic molecule, right? You can pick your favorite, but I'm just going to be generic. We're going to just call it AB. Could be HCl, H2, HBr, N2, O2, F2, whatever you like. Okay. And let's set up the problem. Right, we've got an atom A. We've got an atom B. Right, and they've got some distance between them. Right? We'll just say that the distance between the two atoms at the moment is L for length. Okay. And we want to think about the motion of these two atoms. We know that they're bonded together, right? They're a diatomic molecule, but there's some bond between them. And what I want to think about is that as the motion of that bond, the atoms connected in a bond, how they move together, right? So they've got some tether between them. Right? We'll just think of that bond between them, a sharing of electrons, as a tether that connects the two. Right? So we've got some tether. Like this, that connects the two atoms. Okay, and we're going to treat this like a spring, right? So we're going to think that the bonds we're going to treat them like a spring, right? Why do we choose? We'll think about why springs and why not we think about them as rigid objects, or why not we use another method? Well, springs have the characteristics, and I'll bring up my spring on Thursday. I forgot to bring it, and bring yours if you'd like. Springs have all the characteristics that a bond should have. We have an appreciation that if you don't touch a bond, just leave the molecule alone, there's some average distance that it likes to be, right? We say that in benzene that the carbon-carbon bond is 1.35 angstroms. It just has like an equilibrium bond. And in fact, that's what we call it. So that's a nice thing. Springs have some nice properties. So let's write those spring properties. Right? All springs exhibit an equilibrium length at rest. Right? They don't just immediately compress into nothing, right? Springs just kind of have a natural state, which we'll call L naught, right? The equilibrium length of the spring. Right? And the important thing about a spring is that it follows if you think about how if you stretch a spring, what does the spring want to do? It wants to compress. So as you apply a force outwards, pulling the spring apart, there's a force being created that wants to draw the spring in, right? It resists your motion, and vice versa. You stretch the spring out, or sorry, if you compress the spring, there's a motion outwards to expand the spring. There's that compression, that kind of compression motion that occurs, right? So there's a force that acts, the spring has a force that acts on itself as you displace it from equilibrium that drives it to try to close it or to expand it, depending on which way you stretch it. So the spring exerts a force exerted upon stretch. And the nice thing about this, the force is that it's very simple. We say that the force is equal to some constant K times a linear function of the displacement. Right? So it's a linear function of displacement, meaning that if we stretch it 2 times longer, the force to compress it is 2 times stronger than it was before. Right? It's a linear force. That's the best kind of force. We know how to work with lines. Okay. The minus sign comes from the fact that the force, when you stretch it, when this is positive, the force is negative, wanting to bring the spring inwards. So there has to be a negative. All right, and K is a constant. Right? It's a spring-dependent constant. We call this the force constant. Right? There's a couple different terms. Maybe if you learned springs in Physics 1, they might have called it the Hooke's law constant or the stiffness. Right? And it tells you, again, basically how much force the spring exerts as you stretch it some distance. right? There are some stiff springs. Those are like the ones that are in your engine, like a valve spring in your car. Those are really, really stiff. Take a lot of energy to compress them. And then there's a slinky, which has a very, very small K. It's very floppy. It's so floppy that gravity stretches the spring out, right? A slinky doesn't have enough restoring force to support itself against gravity. Right? So if K large, stiff, K small is what I like to call a floppy spring. And those are actually chemical terms we call bonds that have small force opposites, floppy bonds, and ones that have strong large K stiff bonds. They're actually, I wouldn't call them chemical terms, but they're certainly terms that chemists use to describe bonds. Okay, so that's really nice. Right, so remember that what we want to do ultimately in quantum mechanics is we want to take these physics and we want to convert them into an operator that we measure on a wave function. And that operator, we want to calculate the energy of this system. That's ultimately our goal, to calculate the energy operator. And the energy operator has a kinetic energy and a potential energy. Right? So we need a potential energy. And we can get the potential energy from Newton's laws. So Newton says that the force is equal to minus the potential energy divided by, the derivative of the potential energy with respect to x. And so we could say that the potential energy is just equal to minus the integral of the F, the force, integrated over the space. We can integrate it from L naught to L, right? We're going to stretch the spring, L naught to L. Well, that's really easy. F is just a linear function in L. We just get L squared back. Right? And so immediately we get that V of X is equal to 1/2 K L minus L naught squared. Right? Is a quadratic function. All right. So now we have an interesting potential energy that we're going to add in our Hamiltonian eventually. Different than the particle in the box. Remember, the particle in the box potential was 0 inside the box and infinite elsewhere. This is only infinite at infinite length. So what that means is that effectively there are all possible lengths of this spring are accessible. We just have to have enough energy to get them there. Right? We have to stretch it or compress it enough. Right? And that potential energy goes as the square. So now what we have is a potential where, in some sense, the boundaries of the potential are frequent or energy dependent. Right? Higher your energy, the wider your potential is, because the probability gets larger. So let's look at that. So let's just get like a general sense of what this looks like. So for particle in the box, we have a potential energy surface. We could say that it's centered at L0. And there's always some limits, right, where the potential energy is 0 within those limits. I'm gonna make that green, right? So it's 0 within those limits. And then the potential energy goes to infinity at the boundaries. Goes to positive infinity. And so within the side, the potential, within the walls of the potential, the particle doesn't even see the walls. Right? As long as it's in the middle somewhere, the walls don't really affect it. No matter the energy, right? In some sense, no matter what the energy of the system is, of the particle in the box, it sees the same potential, the same wall, all the way up. Right? Right? So the particle acts freely in here, and then psi is 0 on the outsides, right? There's no wave function on the outside. Now let's look at the spring now. We now have a potential that is a quadratic potential, a parabola. Right? And let's just imagine now I give the system some energy. Right? I'm in some energy level, some energy state inside this potential. Maybe here, or here, or here, some energy, right? There's a couple different energy choices. For instance, right? And now imagine I set my spring, I give my spring that energy, right? And now it's going to bounce. You can kind of imagine it's at this fixed energy. And now think about the potential. The potential is now differently sized for different energy levels. The potential gets wider. The box gets wider. So it becomes less confined as the energy increases. So if you think about it, right? If you think about these as like particles in the box, right? We have one that looks like this and one that looks like this at this energy. And then we have one that looks like this at this energy, right? The potential gets bigger as the energy increases. So here we have an energy, a total energy dependent potential, right? And so that means because energy can take effectively any value, we know that it's going to be quantized eventually, but we know that it can be any energy. There's nothing stopping me from going to infinite, right? And so this potential exists, right? There's only two limits. The potential has to exist on basically any x should be allowed. So potential exists on x within minus infinity and plus infinity, right? Whereas this potential wave function, which means that the wave function exists in the space of minus infinity to infinity. Or I shouldn't say that. I shouldn't say that x exists here, but here x only exists between minus L and plus L. Right? So there's a finite space that the potential spans in particle in a box. But the potential in the harmonic or the spring exists infinite. It exists at all points. Of course, it becomes harder and harder and more energy is required to stretch it more and more. There's nothing stopping me from stretching that spring. Something may bother you about this, though. Imagine L naught is, let's say, a length of 1 meter. And so the center of the potential, the spring wants to rest at 1 meter in its setup. Just equilibrium, regular spring hanging out at 1 meter. And what this is telling me is that I can apply energy and I can shorten it by compressing it, or I can lengthen it by expanding it. It takes equal amount of energy to do either motion. So if I if I expand the spring, the potential energy of my spring continues to increase this way out to infinity. But if I go backwards, imagine now what's happening. I start at 1 meter, and then I go to 0.9 meters and 0.8, 0.7, I continue up. This potential continues on to negative infinity as well. So eventually I'm going to hit L equals 0. And then I'm going to hit negative L's. And what the hell does that mean? Okay. So we can already tell that there's some limit to this because physically this potential can't exist from negative infinity to positive infinity because having a spring length of 0 is impossible. And obviously, if we take a slinky and stretch it meters and meters and meters, it'll break eventually. Okay, so this is not a global approximation of a spring. Real springs cannot have L less than or equal to 0 or L going to infinity, right? Because L less than 0 means, I don't know how else to explain it, right? If L is length of our slinky is 0, it means all the matter is touching itself, right? It's all on top of each other, right? Let me just say matter has size. And here, springs break. Okay, so this potential isn't globally true. It only works for certain stretching. And so what we're going to say is that we're going to say that this is roughly true, that Hooke's law, did I call it Hooke's law earlier? I did not call it Hooke's law. So this formula, Hooke's law, Hooke is the guy who invented this. Hooke's law is valid only for L lengths near L naught. Right? So we're just going to assume that we're just going to think about this theory as working perfectly for very, very small displacements, but we know as we go to further displacements, it starts to break down. We'll actually think about where that breaks down. And we can actually make a qualitative estimate of it. And so we're going to think about, this is how, what we're going to say is that the Hooke's law is how a bond acts locally around equilibrium. So if we take a bond, like a benzene bond, and we stretch it to twice its length, it's not going to be a valid model for that system. But if we give it just a little kick and get it to vibrate just a bit, it might be valid. So let's just keep that in mind in the back of our head, that eventually this starts to break down and we'll need to fix that. Okay, so let's do a little bit of physics now. Right? I want to think about the behavior of this spring classically first. If we can understand how it works like a slinky, maybe that'll give us some hints for how it works quantum mechanically. We'll do the classic part today, and then next class we'll do the quantum mechanics. Okay, so let's set up our problem. Let's just do an old-fashioned physics problem. I'm going to skip some of the details. But let's just get an idea of how this works. Right, I'm going to define a coordinate system, X. Right, I'm going to put two atoms in that coordinate system, A and B. Right, and I'm going to give them coordinates X sub A and X sub B. Okay, the distance between them is L, just like before. Okay, and I'm going to define a center of mass for the system. So I'm going to just draw a fake bond between them, just kind of a dashed line. Right? And I'm going to draw a center of mass between them, center of mass, right? And I'm going to define the center of mass to be x equals 0. Okay. So the center of mass coordinate, so for the first thing we're going to do is we're going to shift to center of mass frame. Right? And the center of mass coordinate is equal to the mass of A times XA plus the mass of B times XB over MA plus MB. Okay. So that's this position, and I'm going to assume it's 0 in this thing. So I'm going to shift everything so XCOM is at 0. Okay. And then what I'm going to do is I'm going to transform. So the way that we can start thinking about this vibration is B and A moving separately, independently from each other, relative to the center of mass. Okay. So the way the spring is going to move from in this perspective is B is going to move and A might move some direction, and they're both going to move independently relative to the center of mass. Okay, that's what a stretch looks like. A compression will look like A and B both moving away at some distance. The heavier atom, because it's at the center of mass, the heavier atom is going to move less than the lighter atom, things like that. So that's just center of mass physics. That's kind of a frustrating thing for us to calculate. The idea that you have two objects that are moving independently of each other. So we're going to simplify this problem with a change of the observer's point of view. We're going to change from the frame of reference of the lab This is the lab frame of reference. I'm looking at two balls on a spring moving back and forth. And I'm going to change my point of view, my observer's frame, to standing on top of one of the atoms and watching the other one displace relative. All right, so I'm going to change my point of view. Change to molecule fixed or to atom fixed. All right, so the idea is I'm going to stick a little guy here. There's my little guy. And he's going to watch B move relative to A now. Okay, so A is going to be stationary to him, and B is going to move relative to him, like the moon and the Earth were on a spring, and the moon is bouncing back and forth, which was crazy, but you can imagine the idea. It doesn't look like the Earth is moving from your perspective. It looks like the moon. Okay, so after the change 2, the problem we actually have now, you could say, is the spring is now attached to a fixed wall. We have a spring now, or spring, of length L, and it's connected to a single mass, mu, where mu is the reduced mass. And mu is equal to MA MB over MA plus MB. Okay, that's a really nice formula to remember. If you guys forgot the reduced mass formula from many years ago in physics. It's very common in chemistry for us to use this. Okay, so now we have a system. We have this mu that has a spring of length L. I should say rather L minus L naught. And it has some stiffness K. Okay. So now what we need to do is solve Newton's laws for this. Okay. We're going to solve Newton's laws now. All right, so now we apply Newton's laws. Which is that F is equal to MA. Okay. The force, as we know, is minus kx. So we have the formula that the mass times the second derivative of the position with respect to time, that's acceleration, minus k times x of t, which is a function, x of t. X is now a function of time, is equal to 0. Right? Which implies that we could write this as minus, what I could say now, let me write this again, that the second derivative of whatever the position is with respect to time is equal to minus k over m. Sorry, m here is mu, I apologize, because it's the reduced mass. So k over mu times x of t. Okay, so whatever motion of this spring, which is x of t, whatever it's satisfied, you take two derivatives of it and you get the same function back. And we've seen that one before, haven't we? Right? We already know the solutions to this. Take two derivatives of the function, get the same function back times the number, a sine or a cosine. Right? It can't be e to the x because that doesn't oscillate. It has to be an oscillating function because as we know, a string goes back and forth. But it can't be e to the x. If it were e to the x, it would just go flying. It's not a very good string. So x here has to be a sine or cosine. We've already seen this. This is the same thing as writing, right? This is the same solution as writing e squared psi of x dx squared is equal to k times psi. Right? It's the Schrodinger equation. We call this the wave equation. Right? There's a reason why Schrodinger called the Schrodinger equation, or called the solutions of it, wave functions, because they mimic the solutions of the wave equation for our spring. or any other type of wave. Right? Same formula, same physics, except it's in space instead of time. So we can already write down the formulas for this. There's sines and cosines. The choice of sine or cosine depends if we start the system at t equals 0 stretched or at equilibrium. So we care about equilibrium. Right? So the solutions of this, I'm not going to go through the math, but it's very similar to what we did with the particle in the box. We have to normalize the function and solve for the boundary conditions. Right? And we get that x of t is equal to some number a times cosine omega, the frequency of the vibration, t, plus b sine omega t. And what is omega? Omega is equal to the square root of the force constant divided by the mass. Right? Right? This is, of course, the relevant number. What this says is that when we stretch the spring, we'll look at the math a little more carefully, but the idea is that we stretch the spring bounces, compresses, right? It moves through equilibrium and compresses back, and then bounces back out, and then bounces back in, and bounces back out. So the displacement of the spring should just be a sine or a cosine function. And the frequency that it vibrates at is a function of the mass on the spring, therefore the mass of the atoms, and the stiffness of the bond. All right, so we call this the harmonic frequency. I'll rewrite this on another page. We'll look at it more carefully. Right, and this is exactly the formula that people use to tune piano strings. Piano wire. Piano wire has a fixed stiffness. Right? In order to get your omega to be 440 hertz for your first A note, for A1, right? You have a fixed K, and what they do is they adjust the tension on the other side of the spring, right? They adjust the tension, which is effectively adjusting the mass. You think about the mass is applying a fixed force due to its weight on that spring, pulling it out. And so that's what the tension on the piano wire does, tension it, adding effective mass to the spring and stiffening it. And they tune mu. And also you could say they kind of tune K because they adjust the tension, whether it's stiff or a little loose, in order to get omega to be 440. That's how we get tunings. So I've seen this if you're a music guy, music person, and you've worked with anything with strings before, this is precisely the way we tune things. And we have fixed K for our strings, and we adjust the effective mass that's at the end of it, right? By tuning the tension of the spring. Okay, so let's look at the physics of this a little bit. Now let's see if we can come up with some nice conclusion about how this works. I want to kind of just like highlight the properties of a classical spring because I want to show you next class how the quantum mechanical spring breaks all of those properties. The quantum mechanical spring works kind of differently than the classical one, but I think it's important to know the classical features first. We can have appreciation for how bonds are different. Okay, so let's draw a potential. Here's my potential. Length, but L not here. Right, and here's my potential energy surface, the nice parabola. Right, and let's just put some fixed amount of energy into this system. I should write that this is potential. So let's put some fixed amount of energy into my system right here. Right? So I've stretched my spring at some amount. Right, so we'll call this, this is my initial spot. We'll say it's L of 0. Okay, so that's where we start our spring. Okay, so we've put some energy into the spring and we've stretched it this far. Okay, right there. So let's think a little bit about the motion of at this point, right? What is the potential energy at this point? Well, the potential energy of that is 1/2 k times the displacement, which is L0 minus L of 0, or sorry, L0 minus. I had to L of 0 minus L0. There we go. So that's the potential energy, right? So we've put some potential energy in our spring. I'm holding it stretched at that position. It has no kinetic energy, right? It's standing still. T is 0 at that point. And then what do? We let the spring go. Let me draw it on another plot, actually. So let's look at the spring as a function of time. Right, here's 0, t equals 0. And the spring, the amplitude tells us where the spring is. The y-axis of this function of time tells us where that mass is. Right? So t equals 0, it's at this point right here, L 0. So this is x of t. We'll say that the origin is at L naught, the equilibrium point. And so that means that this is at L of 0. So this is where it starts, right? And it's a cosine, right? Because it starts at a maximum. We've stretched it all the way. So this is going to go as a cosine. So the spring is going to start to compress, right? Like that. Here's a cosine. So what does that mean over here? We'll call this L of pi over 2, because it's a quarter of the period. Well, what does that mean in terms of the energy? Well, that means that this spring, the spring's length is decreasing towards L naught. Right, so as this evolves, it's running down this potential. Right? And it gets to this point right here. That's at L equals pi over 2 times pi over 2. Right? What's the kinetic energy and the potential energy here? Well, the potential energy is 0 because it's at the bottom of the potential. And because of energy conservation, then kinetic energy has to be what the potential energy was at the initial point, right? They have to be equal. They have to be equal. So here the kinetic energy is maximum. Oh, sorry, this is L0. Right, so you have maximum energy, maximum kinetic energy, right? So as the spring moves through the equilibrium point, it's moving the fastest. And then as the spring approaches the inner point, it slows down. And you end up here now, right? And then by definition, we would end up at minus L of 0, right? It would be the opposite point. And so it climbs back up this potential, and it's right there. This would be at L at effective pi time. It's L of pi. And here again, the potential energy is the same as before, and the kinetic energy is 0, right? And the system returns and does the same thing in the opposite direction. It just keeps going. So this comes back down, goes back up, and bounces back and forth. Okay, so we have energy conservation, smooth exchange between kinetic and potential energy, and it just oscillates like a cosine. All right, so some observations. Is conserved. V is max at the min and max extents of spring. And T is max at L naught. another thing is the important thing is that it never goes past these two turning points. Right? These are the maximum minimum extent of the spring. It never goes past that point. In fact, as the spring, because of friction and stuff, eventually the spring's just going to slowly damp out, and it's never going to reach those points again. Right? So we have these like two maxima and minima points. We call these turning points. Right? And the turning points are never exceeded. We should calculate the total energy of the system to prove that energy is conserved. So let's do that really quickly. Right? Let's just prove that it's conserved. I'm going to go ahead and change the page. All right, so total energy, which we call the Hamiltonian, H, is equal to kinetic plus potential. Right? H, the kinetic energy is going to be, remember, kinetic energy is 1/2 mv squared. Right? We don't know what the velocity is, but we know what the mass is. It's mu. We'll call it v squared. We'll talk about the velocity in a second. And then the potential energy is 1/2 kx squared. Okay. Well, remember that the velocity is the time derivative of the position. So this is equal to 1/2 mu times the second derivative of position with respect to time. Oh, sorry. My bad. It's not the second derivative. It's the first derivative squared. So I got to be careful there. Plus 1/2 kx squared. Okay, so this is the total energy, and that means that it's some number, some total number. Okay, so all we have to do here is plug in our value of x of t, and just to kind of do a little bit of math. So x of t here is, we'll just pick a function. We'll call it, we'll call it a sine k over mu t. Remember, that was our frequency. So now we plug this into our equation, and we get 1/2 mu. And now we have to take the square of the time derivative of our function, right? Because its velocity is the derivative of x of t with respect to t. So we need to take a time derivative of this. That gives us cosine. Gives us a k over mu cosine k over mu t. Right, and then we go 1/2 k, and then we plug in x. That's a sine square root of k over mu t, all squared. A little laggy. You guys may start to note that we're going to have a cosine squared plus sine squared in here. That's going to simplify out. That equals 1, of course. And you're going to see this is going to simplify a lot. You can see now that the mu's cancel out here because of the square. And we have 1/2 a cosine omega t squared plus 1/2 a k sine omega t squared. Right? And you can see that this is going to be equal to 1/2 a squared. So the total energy is this, where a is the amplitude, right? And so this is equal to the extent of stretch. So if system stretched from L naught to L, then the energy of the system is always 1/2 KL squared. I should, oh man, it's lagging today, isn't it? Mm. Okay, so it's got fixed energy. And because it has fixed energy, that means that all it does is just go back and forth between the two turning, right? It's just boring old like oscillatory motion between the two different points, right? That's not very interesting, but it will be interesting in the context of quantum mechanics. What we're going to see, quantum mechanics doesn't follow this property nearly as well. Quite a bit, actually, a little bit more frustrating. It does not behave the way we would like it to, right? But it's important to keep these properties in. So that's our classical spring. Right? It moves like a sine wave. It's got a stiffness that determines the stiffness and the mass on the spring determines the frequency. Those are the two things, right? K, right? The two big things that we have is that the oscillation omega is equal to K over mu. This is important, right? Just to keep that in mind, right? That's some fundamental parameter of our system, right? It tells us how fast the spring moves. Everything else is user input. These are unique properties of the spring. The stiffness of it and the mass that it's attached. Those are the two parameters of our spring. It's the only thing that matters. Okay, so keep that in mind, right? We're going to have to come back and think of what the spring parameter of our quantum mechanical vibrations are. So let's set up the quantum mechanical problem. Right? We're not going to solve it today, but I just want to illustrate the slight why we chose vibrations as the next choice after particle in the box. You see that the particle in the box in particular is a helpful guide for us to think about the part of the vibration more than rotation. Rotation is a three-dimensional thing in a sphere, if you will. You think of an object and you have a vector and it's rotating around. That's a different motion than this. This is still a one-dimensional motion. Right here is just the box is changing as a function of the energy. The box is a function of the energy instead of being fixed. So the harmonic oscillator, in some sense, is kind of similar to the particle in the box. It's intrinsically one-dimensional. Rotation cannot be one-dimensional. Well, it can, but very rarely is it. So let's go ahead and think about quantum mechanics. Remember, our goal again is to calculate the total energy of the system and solve for the wave functions that satisfy that operator. And we've already written the total energy down. It's equal to the kinetic energy plus the potential energy. We've already looked at these, right? We can just grab the ones from the classical example. H bar squared over 2 times the mass, which is mu, times the second derivative of the wave function with respect to position. That's the kinetic energy of the system. And then the potential is just 1/2 kx squared. Yes. Apologies. Right. Times psi. And that should give us some energies. Times psi. Right, let me rearrange this formula a little bit. It says that the second derivative of the wave function is equal to minus 2 mu over h bar squared times the energy of the total energy of the system minus 1/2 kx squared, all multiplied by psi. So this is what we call the spring, I'll get back to that term in a second. So this is our spring, right? Let's compare this to the particle in the box and look at the difference. Right? If we go back to particle in the box, that said that the second derivative of the wave function is equal to minus 2 times a mass over h bar squared times E. Just E by itself, psi. Because remember, the potential inside of the box is 0. So we would have a minus V here inside the parentheses like we have here, but the potential is 0 in the box. Okay, and so we interpreted this as that the wave functions, when you take two derivatives of them, they return the original wave function times a number. Right? This gives us the sines and the cosines. Right? This is the wave equation. Right? And we know that psi for this is cosine x plus sine x with some parameters on top. It looks like sines and cosines, right? We know what that looks like. But here, as you can see, there's a complication to our formula. When we return the wave function, when we take two derivatives of the wave function, we get the particle in the box part back, right? E psi. But the wave function also returns an additional term that's multiplied by x squared. So whatever function this has, it returns the wave-like property that we expect, right? Which is this part of the term right here. But it's modulated by an additional part of the wave function that is position dependent. And when you measure in some sense, the momentum, the kinetic energy of the object depends on where it is in the potential. Well, we know that that's the case with springs, right? What this is saying is that the momentum of our object, right, is equal to the energy minus the potential. And that's exactly what we saw in the classical example. Let me go back again. If our system is at the bottom, it has no potential energy. So any energy that it has is all kinetic energy. That's just like a particle in the box. Right? That would be the minus 2m over h bar squared E side on the right. But as the system stretches, remember the potential changes as the system stretches. And so the potential starts to kick in. And then when we're at the turning points, it's the complete opposite. There is no kinetic energy, and it's all potential. So at any point, the wave function which exists on all of these points has to be some balance of those two limits, right? It's either all potential, it's all kinetic, or it's a little bit of both. We have an exchange between the two types of energy. And so that's exactly what we see in the formula. Here, when we take a second, we ask something about the momentum of the object, momentum squared. We get the energy back, and that's just a straight number. It's just a number, because there's only one type of energy in the system. It's just kinetic energy. H bar squared over 2m. But here now we have a competition between the kinetic energy of the system and the potential energy of the system. So that requires our wave functions to look different. Our wave function now has to return an x squared as well when we take two derivatives of it. So cosine and sine will not work here. So I can say for certain that psi of x is definitely not a sine omega x. It definitely doesn't look like that. But it has to look a little bit like an oscillatory function, because this half of the left side of this equation looks like the wave equation. So there's some oscillatory behavior, but there's something else going on. And then what the hell is this part of the wave function? The wave function kind of has two different behaviors. Right? It's got two different limits. Right? So we're going to have to be careful about that. Right? It's not going to have the same solutions. So let's try a new guess. So we have to come up with a function that kind of looks like a wave, right? Let me write down one more wave. Right? It could also look like e to the ikx, right? It could be a complex wave. Right? But we need it so that the argument inside this oscillatory function, that when you take derivatives of it, you get x's down, right? So x can't be linear in the exponent, because every time you take a derivative, you just get ik back. The x disappears. So there has to be something other than x in the denominator. It has to be a higher order. If it's going to look like a wave, it has to have a higher order of x inside the exponent. So here, let's do a guess. So just like before, let's make a guess. All right, and it's probably not obvious. It's less obvious. That's why I'm not going to have you guys guess it, because it's a little less obvious. But what I'm going to do is I'm literally going to go into a book of functions, just like I did before. We picked out the simplest functions that give us the properties that we want. There is a very, very simple function that gives us the properties I think we want. That's a really well-known function, but not one that you immediately think of. Right, so we're going to make a guess. We're going to make that the wave function is ae to the minus kx squared. I'm going to add an x squared in there instead. Okay, what does this function look like? Right. So at x equals 0, this is at a. Right. So the peak of this function at x equals 0 is a. Right. And then as x goes to either positive infinity or minus infinity, it goes to 0 because it's exponentially decaying. And then around x small, it looks like a negative parabola. It's like a negative parabola. So near x equals 0, it looks like a parabola going down, and then it exponentially decays out. Something like this. Like this. We have different names for this. This is a well-known function. The statisticians call this a normal distribution. Mathematicians and physicists call this a Gaussian function. We'll call it sciences. Do you guys know what normies call this? What's that? Bell curve. That's right. It's a bell curve. We'll see if that works. Right? What do we need? Well, first of all, it needs to be normalizable. So it needs to integrate to 1. Right? But that means that the integral of psi squared dx from negative infinity to infinity is 1. All right, so let's set that up. Integral minus infinity to infinity of a squared e to the minus 2kx squared dx. I just squared the function. Okay. You guys probably don't know how to solve this integral. But this is one of the first integrals you learn when you learn integrals that aren't easy to solve. It has a really well-known formula. I'm going to put it over here on the side. The integral of e to the minus kx squared dx from minus infinity to plus infinity is equal to the square root of pi over k. Can't get any easier than that. I mean, I guess unless it was pi over k, that would make it easier. Really simple. It's kind of cool that, once again, amazing part of math that you get an exponential function, and when you do something to it, you get a pi out. Clever. Turns out the reason why is because you integrate this in polar coordinates. It integrates, you get a pi out from it. Right, and so we can just plug and chug with this integral. This is going to be equal to a squared pi over 2k. Is that equal to 1? All right. And that means that a is equal to 2k over pi to the 1/4 power. Okay, so our result is that psi of x kind of looks like, we're not really sure exactly what it looks like, but we're guessing it looks like 2k over pi to the 1/4 e to the minus kx squared. Okay, so there's one property. Remember that failed when we did sine and cosine and e to the x. That was the first thing that failed with our guess, was that it wasn't normalizable. And that most of those diverged, or they didn't have defined integrals. This one has a beautifully defined integral. So that's good. So it's normalizable. Good. But there's another one that we have to deal with. Right? The second is that we have to show that when we apply the Hamiltonian to it, we get an energy back times the wave function. Is it an eigenvector of the operator? So does H psi equal to E psi? Okay. This is kind of this is some ugly math. But we want it to satisfy so I'm not going to do the math for you, but what you'll find is that once you apply psi of x, you get the following formula. You get that the second derivative of psi with respect to x is equal to minus the square root of 2k psi of x plus 2k x squared psi of x. Right, so this is our e, and this is our minus 1/2 kx squared. And so this looks like equals psi of x is equal to, or sorry, the right-hand side looks like, I apologize. It looks like e minus 1/2 kx squared psi of x. That's what this simplifies to. And that's exactly what we wanted on the right-hand side from the last slide. Okay, so psi is an eigenvector of our operator. All right, that's good. Okay, so it satisfies the Schrodinger equation. It's normalizable. We have one more feature that we have. They have to be orthogonal. The other one is that the functions are perpendicular. Orthogonal functions. Okay, so imagine that we have two different, right? So we have two different wave functions. Psi1 of x for one state. That's going to be, we'll call that, sorry, let me get it right. 2k prime. Oh, let's just call it k1 or k1 over mu1. Oh, sorry, that's pi. I'm sorry, I can't do my math properly. Over pi to the 1/4 e to the minus k1 x squared. All right, so you've got one state of your system. We're going to say that H applied to psi1 gives you E1, psi1, right? It's got some energy. And then we're going to construct another state, psi 2 of x, which is 2k2 of pi to the 1/4 e to the minus k2 x squared. And we're going to say that this gives me a different energy. Okay. We have two different states of different energies of our wave function. And what the Schrödinger equation says, like the states have to be orthogonal, meaning that they're perpendicular to each other. Remember, you take the dot product of two states in your basis, you get a dot product of 0, they're perpendicular. That means the integral of their product is 0. So what we would get, what we need to have is that the integral minus infinity to infinity of psi 2 star psi 1 dx is equal to 0 unless k1 is equal to k2, and therefore we should get psi 1 star or psi 2 star psi 1 dx is equal to 1. Okay, so that's orthogonality, meaning that two wave functions of a system, when you take a product of them and integrate it, they're 0. They have no similarity to each other. It's the same thing as saying two vectors are perpendicular. Right? That's what we want for our basis functions. Right, so let's go do that integral, right? So let's just go plug them in and see if we get 0. Okay, so that's going to be 2k1 over pi to the 1/4, 2k2 over pi to the 1/4 times the integral from minus infinity to infinity of e to the minus k2 x squared. All right, that needs to be a 2. Times e to the minus k1 x squared dx. Okay. We want this to be 0. Any functions, there should be some value of k1 and k2 that should make this 0. And there should be a value, well, they should be, if they're equal, it should be 1. It's probably not too hard to show that it's roughly 1. I'm not going to say that yet, actually. All right, so this is k1, k2 to the 1/4 times the square root of 2 over pi. And then times the integral from minus infinity to infinity. And then what we do is we just add the exponents, right? This is minus k1 plus k2 x squared dx. Okay. And we know the integral for this, it's just another Gaussian. A product of two Gaussians is a new Gaussian. So the answer to this is k1, k2 to the 1/4 times 2 over pi times pi over k1 plus k2. Do I have that right? Yeah, pi k1 plus k2 to the 1/2 power. And as you can see, this is not equal to 0. It's some number. Okay, so it doesn't matter how, the only numbers that I can choose for this to simplify out is where one of them is 0. Okay? Which means that the function is 1. So it's trivial. So what that means is that these functions, this guess is not orthogonal. Gaussians are not orthogonal. So we're so close. It's got 2 of the 3 properties. Normalizable, satisfies Schrödinger equation, it's just not orthogonal. So the question is, damn, we're so close. We just need one more property. Is there something we can do to this function to fix that problem? So the question is, can I modify my Gaussian functions with something that would make them orthogonal? Well, what we need to think about again is to look at this function, this Gaussian function. It doesn't look like a wave at all, does it? It's just a bell curve. It doesn't have any oscillations to it at all. And what do we know about systems or particles that are bound in states? They act like waves. So the thing that we're missing here is the wave-like oscillation of the system. Right? So we're missing some oscillatory feature. Right? We have to impinge a wave-like characteristic to this Gaussian function. So maybe what we would want, this is not going to work, but so the trick is e to the minus x squared has no wave properties. So our proper wave function, right, it should look like AE, oh, sorry, let me get rid of that. It should look like some number AE to the minus kx squared, but it should be multiplied by some oscillatory function. Right, and that is also orthogonal. So this installs orthogonality. So it's a little tricky. We have to think about what oscillatory function to append. Right? And it has some wave-like properties. And if they're wave-like properties, then the orthogonality actually just kind of comes from the math. The fact that they're oscillatory helps the orthogonality because that's kind of how waves work. Waves are typically orthogonal. Right? We're going to answer this question next class, but let's just kind of think a little bit about what this should look like in our potential. Right? So we know that this dominates for x going to infinity or plus or minus infinity, right? That term is going to be really, really small at big X. Right? And it looks kind of like 1 in the middle. All right, so I know that the wave function is going to go to 0 at minus infinity and plus infinity. So let's go ahead and just draw a potential. And I'm going to set my system at some energy level. All right, so here's my energy. The energy of total energy of the system. Right? And I've got some wave function that exists at this energy. And I know at long distance, it's going to exponentially decay. Right? So I know that, and it's outside. So I know on the outside, this is going to decay only at infinity outside of the potential. Right? And I know that inside the potential, right? If we go back to our formulas here, inside of the potential, where the potential energy is small, we mostly have oscillatory wave-like behavior. So inside the potential, it should oscillate. So what we would hope to expect is a function that kind of looks like this. Like this. Right? And so this is our e to the minus kx squared term on the outside. And then inside of here, we have an oscillatory function. Right? Something that looks like sine or cosine. We're going to find out that it can't be either of them. But we can come up with another oscillatory function. There's different types. And we're going to find the right one for that solution. Okay, so the wave function of our system should look like this. It should look, the spring is wave-like inside turning points. And exponentially decaying outside. All right. Well, look at the, that's a really big observation, because what this tells me is that there's some probability that the spring is on the outside of the turning point. We've already broken the classical laws. We know that goes e to the minus kx squared, which means there's some probability. The only place where there's zero probability is at infinity. So that means that spring can be any length it wants. But that probability goes down as minus kx squared. Okay, so it's exponentially damp, but it can exist outside the turning point. So it's already Blake's rules. We haven't even done the math right. We've already broken rules. So what we're going to do next class is we're going to come back and think about this function, come up with the right solution for it, and get energies and all the properties. Okay, have a good one, guys. Thank you.
So you only walk away home. So in your but I don't want to leave alone. It doesn't really go on with savings. Yeah, like in that.
Yes, but not in that drawing. I mean, that works. What I want you to draw.
Yeah.
I always have you guys write energy level diagrams, and I really just don't think I just want straight lines. Just
Okay.
do it on a piece of paper.
Okay, because I don't know if I had.
It doesn't have to be precise, right? You can just write.
I just have to look up like what things they put into the diagram. Oh, yeah.
Oh, so here I think you have 3.
Yeah.
Here you have 2. Or you have 2 here. With 1 here, even 4. You have 3 up there. It looks like this. And then you put the energy.
Let's see, guys. Right. Okay. Thank you.
You got it.
Thank you. Thank you. I got scared because it wasn't linear. It was just linear. I'm like, is this
It
right?
should be.
Yeah, that makes sense.
The energy is equal to h squared n squared, so it should be linear and n squared, right?
Yeah, that makes sense.
Yep.
Thank you.
Yep. Yes.
I just want to for me, I'll probably be joining Thursday on Zoom,
Okay.
just because of the
I
company.
saw you on Zoom right now too.
I did because of the angle that I was on.
Oh, you
I
can see the screen?
board, so I wanted to be able to write, and then my computer was glitching, so I was like taking notes as I was going.
Okay, that's fine.
Yeah, okay.
All right, thanks, Jay.
So